Hey everyone, welcome to the video. Have you ever wondered how reliable those average statistics you hear about are? In the world of data analysis, there's a hidden force at play called sampling error. It's the gap between what we see in a small sample, like a class average score, and the reality of the entire population, all student scores. This video dives into a powerful technique called the Bootstrap method. It tackles this sampling error head-on, helping us understand the uncertainty surrounding any statistic. Buckle up, because we'll explore what Bootstrap is, why it's so valuable, and how it works through a clever method called sampling with replacement. Now, imagine developing a new fertilizer with limited plant test sample size, N. Bootstrap tackles this by creating simulated samples, replications of your original dataset D using a key technique, sampling with replacement. Unlike traditional sampling, we can draw the same data point multiple times, mimicking real-world variability. This allows us to estimate how much the results, like the average yield increase, represented by a statistic of interest, might differ if we repeated the experiment with various samples. Traditionally, researchers might conduct experiments multiple times to assess variability, standard error. But this approach is impractical and time-consuming. Bootstrap offers a solution by leveraging your existing data and the power of sampling with replacement. This is particularly valuable for complex statistical methods, where traditional calculations for standard error become cumbersome. It simplifies the process of obtaining standard errors and confidence intervals, providing a more accessible way to understand the uncertainty in your estimates. Let us illustrate the Bootstrap process with a clear example. Imagine you have data representing exam scores. Your objective is to estimate the average score and its potential variability. Here are the steps in which Bootstrap aids in this, emphasizing the replacement method. First one is sampling with replacement. We draw samples of the same size, K, as the original dataset, the student scores, from the original data, D, allowing for duplicates. This creates a new bootstrapped dataset, D*. Then comes repeat and calculate, in which we repeat this sampling process numerous times, for example 1,000 repetitions, to generate a collection of bootstrapped datasets, D1, D2, D*K. But in our example, it is possible to create only 4 bootstrap datasets as we have 4 observations initially. Third one is distribution analysis. For each bootstrap dataset, D*K, we calculate the statistic of interest, like the mean exam score, μ*K. This yields a distribution of means. Variability estimation. By analyzing this distribution of means, μ1, μ2, μ*K, we can estimate the standard error of the mean and construct confidence intervals. These provide insights into how much the average score might vary if we selected different student samples. Bootstrap extends beyond estimating the mean's variability. It's applicable to various statistics, such as proportions, medians, regression coefficients. This makes it a valuable tool for comprehensive statistical analysis. By understanding Bootstrap, particularly the power of sampling with replacement, you gain deeper insights into the uncertainty surrounding your data, empowering you to make more informed decisions based on statistical significance. With this, we have come to end of this video, so before ending, let's see how well you've grasped the concepts. Pause the video and take a moment to answer these questions. And make sure to write your answers in the comments below. Thanks for watching.